It's time to learn a new test. This one is called the alternating series test. And we're going to start by revisiting the harmonic p-series, which is 1 over n, which of course we know to diverge. But suppose we wanted to alternate the signs. What we would end up doing is taking 1 over n and making every other term negative. So instead of adding 1/2, we'll subtract it. Then we add 1/3 and subtract 1/4. We add 1/5 and we subtract 1/6 and so on. And this is called the alternating harmonic p-series, which just means that the signs of every other term alternate. And in summation notation, we would say that it is the summation from 1 to infinity of -1 raised to the n plus 1 times 1 over n. So we've added in this alternator. Notice that if I plug in 1 into my alternator, I get -1 squared, which makes my first term positive. So let's take a series of partial sums of this new series. So we'll start on a number line with the endpoints of 0 and 1. And the very first term is 1. And so we are going to have a first partial sum here at 1. Then I subtract out 1/2. So I'm going to have 1 minus 1/2, which is 1/2, as my second partial sum. Then I'm going to add on 1/3. I know that 1/3 plus 1/2 is 5/6, and that is my third partial sum. Then I subtract out 1/4, and my fourth partial sum sits here. Then I add 1/5, and my fifth partial sum is here, and then I subtract 1/6, and this is my sixth partial sum. So what you should be doing is seeing this visual of convergence. So we start with a sum of 1, we go down to a sum of 1/2, we then go up, and then we go down, and then we go up, and then we go down. Well, guess where the actual sum is going to be? The actual sum is going to be somewhere in between these last two terms that we added. And no matter how many terms we added, the sum will be in between the last two. So we took a divergent harmonic p-series and we made it into a convergent series by alternating the sign of every other term. So we created what's called an alternating series. And here we'll learn about the alternating series test. And the alternating series test occurs anytime you have an alternator in a series. And there are several alternators we will use, including -1 to the n plus 1, -1 to the n minus 1, and -1 to the just plain n, and then one that you wouldn't expect, which is cosine of pi n. Because if n equals 0, cosine of pi is -1. Excuse me, if n equals 0, cosine of 0 is 1 over here on the unit circle. If n equals 1, cosine of pi is -1. Cosine of 2 pi is 1, cosine of 3 pi is -1, and I keep toggling to the either side of the x-axis where it intersects the unit circle. So cosine of pi n is an alternator. People often ask me, what about sine of pi over 2n? And that is not an alternator from the sense that we are going to use, because if n equals 0, we have sine of 0. If n equals 1, we have a 1. If n equals 2, we go to 0. If n equals 3, we go to -1. So you go in this rotation from 0 to 1 to 0 to -1. The alternator can only go from 1 to -1 to 1 to -1. So the fact that we're adding in these zeros nullifies this as an alternator for our purposes. So we really just use these 4 alternators, and you will recognize them in a series, which makes this series easy to apply because you'll see the alternator and know that you're going to apply the alternating series test. The alternating series test says the following. If the 3 conditions below hold, then the alternating series converges. We also have this IFF, which is if and only if. That means this is a biconditional. If the 3 conditions hold, then the series converges. And if the series converges, then these conditions must hold. So let's talk about these conditions. First, every term in the underlying sequence must be positive. So that's when you ignore the alternator and you just look at a sub n. Those terms must be positive. Next, the terms in the sequence must be decreasing as n goes to infinity. And to be clear, we only care what happens in the long run as n goes to infinity. If the first two terms hold steady or maybe even go up, that's okay. What we really care about is as n goes to infinity that the terms decrease. And then last, we need to show that the limit of the underlying sequence is equal to 0. So let's do an example. First, we have our a sub n, which is this, n squared over n cubed plus 1. If I plug in n equals 2, I get out a positive number. If I get n equals 3, I get out a positive number. So my underlying terms of the sequence a sub n are greater than 0. The first condition is met. Let's look at condition 2. Are these terms decreasing? Well, let's plug in a couple. If I plug in 2, I'm going to get out 4/9. If I plug in 3, I'm going to get out 9/30. If I plug in 4, I'm going to get out 16/65, and so on and so forth. And what you'll find is that these terms do decrease as n goes to infinity. So that condition is met. And then last, let's check to see if the limit as n approaches infinity of our underlying sequence n squared divided by n cubed plus 1 equals 0. And it does because I have a larger degree in the denominator. Therefore, by the alternating series test, this series converges. So let's take a look at another example. Once again, alternator is present, so we have an alternating series. So let's take a look at 1 over n squared. First of all, are all of the terms positive? Yes, they are. Second, are these terms decreasing? Well, the terms are 1, then 1/2, then 1, then 1/4, then 1/9, then 1/16, etc. They are decreasing, so this condition is met. And then last condition, what is the limit as n goes to infinity of 1 over n squared? That limit is 0, so that condition is met, and therefore this series converges.